In this lesson, we're going to be looking at the topic of spanning sets. But in order to address that, we first need to deal with the idea of linear combinations. This is actually not new. We've been doing linear combinations of vectors already, but it's worth having a reminder of that. So if I have two non-collinear vectors, meaning they are not parallel, they cannot be arranged to share the same line, they're not parallel, vectors u and v. A linear combination just means I take some scalar multiple of the first vector and I add to that a scalar multiple of the second vector. And remember, these scalars can have any value. They could be zero, they could be positive, they could be negative. So to illustrate that, the first thing, and this leads into our discussion of spanning sets. So consider the implications of what we're going to do here. We're going to show that this vector, 423, can actually be written as a linear combination of these other two vectors. Now we've written things like this vector very trivially as, for example, I could write that as 4i plus 23j. So we know we can write this as a linear combination of the basis vectors, the I and j basis vectors. But what about these kind of awkward and odd vectors? What about that? So let's go ahead and try that. Now, if that's the case, then what we're really trying to show is that the vector w is a linear combination. So it's going to be some scalar times u plus another scalar times v. But we already know what w is. It's 423. And u was given to us as negative 1, 4. And b was given to us as v was given to us as 2, 5. So from this, I can actually break this out into two separate equations. If I wanted to, I could write this in terms of the basis vectors. So I could say that this is 4i plus 23j is equal to a multiplied by negative I plus 4j plus b multiplied by 2i plus 5j. I could do that if I wanted to. The important part, though, is for us to recognize that the x components, the things that are along the x-axis, have to be equal to each other. So we get from this that 4 must work out to be a times negative 1, which is just negative a, plus b times 2, which is plus 2b. And that actually is our first equation. We're going to end up forming a system of linear equations here. My second equation is that 23 must be equal to 4a plus b times 5 is 5b. I'll call that equation 2. Usually I find elimination is preferable. So what I'm actually going to do is I'm going to take equation 1 and I'm going to multiply it by 4. I can see my equations are already in the same form. So equation 1 times 4 gives me a 16 here. 4 times negative a gives me negative 4a. That's what I was really interested in there. And 4 times 2b gives me positive 8b. So when I add these together, so now I'm going to take this third equation and I'm going to add them. 23 plus 16 gives me 39. 4a minus 4a gives me 0. And 5b plus 8b gives me 13b. Then I divide both sides by 13. I end up with b is equal to 3. And then from there, I'm going to sub b equal 3 into equation 1. So I end up with 4 is equal to negative a plus 2. And then I'm going to make this substitution 2 times 3. I'll bring the a over to the left side, and I end up with 6 minus 4, or a is equal to 2. So I've got my answer, and I now know, therefore, the vector w is equal to, and just to get these correct, it's a times u plus b times v. So a is 2 times u plus b is 3 times v. If we wanted to, we could also do a left side, right side check, which of course that's valid for any system of linear equations. We could always, so we could do a left side, right side check on equation 1 and 2 and make sure that those actually work. Okay, so keep in mind what we just showed there, because I'm going to be looking at that from a slightly different perspective now. So we've already done quite a bit of work in this unit on the two basis vectors, which are the ij vectors. Those are the basis pair, that's the basis pair for the Cartesian plane. Now what if I just gave you another arbitrary pair of vectors, just like I did in that previous question? So this is the vector 1, 2, this is the vector 2, 1. Can we use these to describe an arbitrary position in R2? Now in the previous question we showed that these could be used to describe a particular point, and I'm actually going to do the same thing here. This time I'm going to do it in an illustrated way, so I'm not going to do it one piece at a time with you. I'm not going to do it by hand. So we know this works with the ij vectors, but what about these two? These are kind of awkward. So with the ij vectors, here's our point at 6, 6. Well, we take 6 copies of the I vector and 6 copies of the j vector, and we end up at our point. And that makes perfect sense to us. We've been using the I and j vectors this whole time because they are the basis vectors. We can make any vector in R2 using these vectors. But it turns out I can actually do the same thing with these vectors a and b. These vectors they're not unit vectors, they're not orthogonal, meaning that the angle between them is not 90 degrees, but the important properties they have here are that they are non-collinear, they don't lie along the same line, and they are non-zero, which is obvious, they both have length. And although I chose this point for convenience, so that it was actually going to be an integer multiple to get there, it turns out any point on the Cartesian plane could be described by those vectors a and b. And that leads us to our idea of a spanning set, which is that any vector in R2 can be written as a spanning set, or written in terms of a spanning set. Now the spanning set we're going to be using most often are the I and j vectors, and those are known as the basis vectors. They are essentially the simplest spanning set that we can deal with. But we can have any pair of vectors so long as they are non-zero and non-collinear. So they have to have length and they can't lie along the same line. And if that's the case, then we can create a spanning set. So how do we prove that we have two vectors here? How do we prove they form a spanning set? Now in this case, I'm not trying to find a specific point like I did in my first exercise. Now I'm trying to find something generic. So what I want to do is I want to set a generic vector xy, and I want it to be the linear combination of these two vectors. And as I said before, sorry, I'm supposed to move to the next page. So let's try that again. My generic xy is equal to a times 2, 1 plus b times -3, -1. And that is where a and b are just some scalar values. That means my x coordinate is going to be a times 2, or 2a, and my other one is going to be b times -3, which is -3b. There's my first equation. My second equation is y is equal to a times 1, which is just a, and b times -1, which is minus b. That's equation number 2. Now I have too many unknowns here, and that's one of the reasons why I'm going through this exercise with you, is because you need to see, well, how do I interpret this? Now I take a look at this, and as far as I think what I'm going to do is I'm going to take equation number 2 and I'm going to multiply it by 2, and I'll put it here. So that gives me a 2y. And the reason I wanted that is for the 2a here minus 2b. And then what I'm going to have to do is a subtraction to get rid of that 2a. So I end up with x minus 2y on the left side. And when I do my subtraction here, I get negative 3 minus negative 2b. But that's the same as plus 2b. So that's going to be minus or negative b. Notice that I've gotten rid of a. I've eliminated a. So if I reverse the order of this, I could write this as b is equal to, and I bring these two terms to the other side, negative x plus 2y. Now you might ask, well, does that really help me? Let me take it a little bit further, and I'll come back and explain to you why that does help. So now that we've got this, let us use equation number 1, and I'm going to eliminate the b. So I end up with x equals 2a minus 3, but I'm going to substitute my b value here. Instead of minus 3b, I'm going to say that's negative x plus 2y. And so I end up with x equals 2a. Negative 3 times negative x is plus 3x. Negative 3 times positive 2y is minus 6y. I want the a all by itself, so I'm going to bring everything else to the other side. So I get x minus 3x is negative 2x, and this negative 6y becomes positive 6y, and all of that is equal to 2a. Divide everything by 2, and I end up with a equals negative x plus 3y. Now, when I do this, what I have shown, because now we're down to important results, what I have shown is that for any xy, and remember this is a point in R2, so I'll say for any xy in R2, x is a real number and y is a real number. That's what it means to be a point. The x-coordinate and the y-coordinate are real. Sorry, this is a vector, but these would just be the vector components, x and y. And so that means that my a value is going to be a real number, right? Because this is just a real number x and this is a real number y, and so this is some algebraic combination. And my b value is also a real number. This is an x and this is a y. And so for that reason, that means that therefore any x, y can be formed. I can choose any pair, any x and any y value, and I will be able to come up with the a and b value that would correspond, that would produce that. So therefore, the vectors, what are these vectors? They are 2, 1 and negative 3, 1. So the set 2, 1, comma, negative 3, 1, sorry, negative 3, negative 1, form a spanning set. Okay, what if we move into R3? Now in R3, we're not ready to really deal with the idea of spanning sets in R3. So what I'm going to talk about here is if I have a pair of non-zero noncollinear vectors, in R2, those form a spanning set, which means essentially they can be used to represent the xy plane. In R3, same thing is true. If I have a pair, it is only two vectors. If I have a pair of non-zero noncollinear vectors, they will also span a plane. It won't necessarily be the xy plane, which was the case in R2, but they will form this plane. That means that any other vector that lies in whatever plane it is they're forming can be expressed as a linear combination of those vectors. This is a tough one. You're probably going to have to spend some time thinking about this. The corollary to that, which just means that's a mathematical phrase that says, well, if I take this and I think about what's the other way of looking at it, the corollary of this is if we start with a vector and that vector is a linear combination of two other vectors, it must lie in the same plane as those two other vectors. So show that this vector, -9, -4, 1, lies in a plane that is defined by these vectors. And if it's defined by these vectors, it means this original vector can be expressed as a linear combination of these two. So that means that -9, -4, 1 can be written as A times -1, -2, +1 plus B times 3, -1, 1. Now I have to deal with x, y, and z components, so I'm going to end up with three linear equations. -9 is equal to -a from here plus 3b. That's equation 1. -4 is equal to -2a minus b. That's equation 2. And 1 is equal to a plus b. And that is equation number 3. And if I start from there, I'm now going to try solving. I take a look. I'm actually ready to take equation 3 and put it right here. 1 equals a plus b. I add these together. I get -8 equals 0 plus 4b. So I immediately get b equals -2. And now I sub b equals -2 here, so I get 1 equals a plus, and this is going to be b equals -2. And so, of course, I bring that over, and I end up with a equals 3. Turns out I didn't even need to use this one. So I end up with b equals -2, a is equal to 3. Now, these have to work for all values of x, y, and z. So I must perform a check here. Because in particular, I haven't even tested this for this middle equation. So the check that I'm going to want to do is, the best thing to do is just to go back and do a left side, right side on my full expression or my full equation. So the left side on my equation is equal to -9, -4, 1. My right side on my equation is going to be a, but a was equal to 3. So that's going to be 3 times -1, -2, +1, plus b, but b is -2, so that's actually -2, 3, -1, +1. This 3 can be multiplied into each of these vector components. We could use the I, j, and k vectors, but I can also just write this as 3 times -1 gives -3 for the x component, 3 times -2 gives -6 for the y component, and +3 for the z. And then this one, how you choose to do this is up to you. Whether you keep a minus sign here and just multiply in the 2, or whether you multiply in the -2 and turn this into a plus. I'm going to leave the minus sign, and the 2 times 3 is 6. The 2 times -1 is -2, and the 2 times 1 is 2. You have to be really careful when you're doing this. The other thing you could have done is you actually could have gone straight to this line, which is just to take a look at the x components together. That's -3, and that's -6, so that's going to give me a -9. That's -6, and that's +2. That's going to give me a -4. And that's 3 minus 2 is going to give me a 1. And as we can see, my left side is equal to my right side. And so what did I just show? I showed that the vector -9, -4, -1 lies in the plane defined by these vectors. And how did I show that? I showed, what I actually showed was that -9, -4, 1 is collinear to a times -1, -2, 1 plus b times 3, -1, 1. And if it's collinear, or if it actually, I showed that it's equal to, but if that means it's collinear to each of these other vectors, therefore they are all in the same plane. We're going to do more on this in a future unit. And finally, this is actually a pretty simple one to end with. A vector set which is made up of 1, 0, 0 and 0, 0, 1 spans a plane in R3. What is the equation of that plane? So let's go ahead and first of all just put in my axes. So x, y, and z. There's the x, there's the y, there's the z. That's a right-handed orthogonal coordinate system. And then the vector 1, 0, 0, that means 1 unit along the x direction. So I'm just going to make that kind of thick, a thick line with a nice clear arrow on the end. And then 0, 0, 1 is 1 unit in the z direction. And so, what plane does that span? And you can see, well, that's in the x and in the z. That actually spans, I know this is a crude way of showing it, but this spans the xz plane. So that's so this part is the xz plane. And what is the equation of that plane? The xz plane can be described as some x coordinate, a y coordinate of 0, and some z coordinate. So that's the xz plane can be described with a whole bunch of vectors that have these properties, where the y value is always 0. And so the more condensed form of saying that is simply y equal to 0. So the xz plane, and we've discussed this in a previous lesson, has the equation y equals 0. And there is your assigned work for this.